The issue is if you go and ask particle physicists if they want a bigger collider, they're going to say yes.
It's true, Gavin. For a while, I mean, we've never found dark matter. We don't know what it is. None of the experiments built have found any answers.
That's quite true. In fact, we've known about dark matter for maybe 90 years, and people have looked for it and looked and looked. But colliders were never guaranteed to find dark matter. That's not what you build them for.
Why do you build them?
You build them because you want to explore new energy domains. You might get lucky, and it might turn out that in the energy domain you're exploring, a dark matter dark matter candidate pops out. But you would never actually know if it was a dark matter particle or not. You'd know that it's a long-lived particle. Long-lived on a detector scale, it means 10 nanoseconds. Dark matter has to live the age of the universe to be dark matter. Now, that's not to say that some of my colleagues didn't say we would find dark matter colliders. Quite a few did. People got carried away. Scientists get carried away like everyone gets carried away. But there were some of us who were actually saying, no, hang on, that argument is a delicate one. That's not why we're building the collider. We might get lucky and find dark matter, but we're building the collider, we're running the collider just to search generically, to search for all sorts of things, searching for thousands of different kinds of things to see if they're out there. And that's the nature of science. You have to explore at some point. If you stop exploring, you stop looking, going places you've never been before, you effectively stop doing science. Now, the disagreement is, where do you go looking? And what I'm saying is that, well, build a new collider, go and look generically at sort of significantly higher energy scales. And at the same time, you know that that collider is going to tell you something about the standard model. You've got a guaranteed discovery as well as the possibility of exploration.
Did you say build a new collider?
Yeah.
So you're in agreement?
Well, no, because Sabine says we should not build a new collider. It's a waste of money, to paraphrase her. And I'm saying, actually, it's a very good investment because we've got a guaranteed discovery ahead of us. And we're exploring new terrain, which is what science has to do.
I mean, it's interesting, we're talking about dark matter as an example of something we have in our cosmological models that actually describes a gap between what the theoretical prediction would be and what our observations are telling us. It is not a tiny minor gap, it's a large discrepancy. And we've invented something called dark matter that we, like the cosmologists, believe exists and that they've been searching for and have not found so far. What is interesting in the context of the history of atomism and particle physics is the assumption is we have something we call dark that must exist if our theory or a model is correct. Then the assumption of a lot of physicists is it must have a particle nature. There must be a particle somewhere that we could just build it. So for me, this combines as an illustration of how the dominance of particle physics and this narrative of atomism is driving research in which the actual solution to what might be why we have dark matter in the first place might be more fundamental than that. That maybe there is something wrong with the original model to begin with. Dark matter isn't actually a thing, it is something that fills a gap in our own models.
Yeah. And actually that's my question, leading on from that, is why do we need a new collider when we already have a collider?
So any collider, the question is tied in part with E equals mc squared. And what you're trying to explore is a certain mass range. M is the mass. And to get to a certain mass, you need a certain energy. And when you have a collider, it's limited in its energy reach. So you build it to go up to a certain energy, and it can't go beyond. And you collect data at that for a while, for a couple of decades. But at some point, collecting more data doesn't get you much further. And the only way you can get further and explore really a new domain is to increase the energy. And that's where you need a new collider.
Right. Sabine, can I bring you in on that point?
Well, that's entirely correct. Yeah, I mean, so the problem is, if you want to build a collider that pushes more energy into those particle collisions so you can create heavier particles, at the moment, the way that it works is that it has to be bigger. And since those collisions create a lot of radiation that you just don't want people to run into, they put those colliders into underground tunnels. And it's really, really expensive to dig such a long tunnel and then put all those magnets in that have to be cooled with liquid helium and so on. So it's really expensive. And I think that's a factor we should not neglect. Now, Gavin says if you stop exploring the high energy frontier, you basically stop doing science. I think that's a little harsh. There are other things you could do to explore the foundations of physics. And I just think that this bigger collider is a little too much money for the little output that it's guaranteed to create. So yes, it's correct, there is some output there. It's pretty much guaranteed to create. It'll tell us more about the Higgs boson and some other particles. But when it comes to those big questions that I think people get inspired by, there's no such guarantee. There isn't even, a particularly good motivation for it, whereas we have those motivations for other experiments. So that's what I think we should do first.
I mean, to use Bjørn's vocabulary, should we be changing the narrative rather than looking at it in the way we've always looked at theoretical physics? Do we do something radically different?
Well, I think we should think a little bit more strategically. So in the past, a lot of breakthroughs have happened accidentally. It was just something that people saw popping up in their experiments. And this has driven a lot of progress historically in physics. Now, the issue is that if you have machines that are the size of, a ring of 100 kilometers or something, you don't discover things accidentally with a machine that size. You have to think very carefully about whether we're going to invest, like $40 billion or whatever the thing is going to cost. You don't just play around with those things. So you have to think very carefully about what kind of experiment is the most promising one to do with the money that we have, because we can't do all that we want. And so personally, I'd say, let's do something else first, see what we find, and then let's go back and think about building a bigger collider when we know a little more, and also when maybe the technology has progressed further so that the thing is not that hugely expensive.
And what kind of direction would you advise going into? Because, for example, with traditional computers, it's very logical, binary, and it's radically different to start researching something like quantum computing. Like, are you suggesting a radically different approach to physics?
No. So people ask me this all the time, and I always give the same answer, which is like, why are you asking me? So I think you should be, drawing in intelligence from all physicists about what can be done in their area, what they think the chances are. Use some intelligent approach to the question. The issue is, if you go and ask particle physicists if they want a bigger collider, they're going to say yes. So that's not a particularly good approach. Now, I could tell you what I would personally do, but this would just be my own personal interest. So I don't think that's the right approach either. You want to hear?
Yes.
So I think we know that there's something wrong with the standard model in that it doesn't include gravity. So I think we should be doing more experiments to probe the quantum gravitational range. And I think it's possible to do this in laboratories. So I've been working on this for some while. There are a few small experiments on that, and they're making slow progress, but there's more that could be done. And there's also, in the area of quantum information, quantum computing, there's more stuff that could be done by the way of fundamental research, that's not getting done. It's very strong in the technology range at the moment, but for what the fundamental research is done, I think there could be more being done.
Gavin.
So the question of what's important is a subjective one. So why do I think what particle physicists do is important? And why do I think the Higgs is worth studying more? Well, to give you an idea, what the Standard Model says is that we live sort of in the bottom of a potential. What that means, imagine you live at the bottom of a hill. How deep is that hill? What's the energy associated with that? The energy is basically you take the sun, the whole of the sun, and you compress it into a shipping container. That's the kind of energy scale that we're talking about when we talk about the Higgs field. That is larger than any energy density of any object we've observed in the universe. And that's what's written in every single particle physics textbook. And we do not have any evidence that what's written in all those textbooks about energy densities of the sun in a shipping container is true. So I say, okay, this is quite an impressive thing that we're writing in our textbooks. Why are we writing it if we haven't actually measured it? And that's that's one of the things that you could do with a future collider. Now, is that important? Is that not important? Well, that's where scientists get together with policymakers, science policy, they get together with governments, and they discuss and they decide, is that important enough to warrant spending the money? And there's a process. And there's no decision yet to build a next collider, but there's a process that is ongoing over a period of a decade, more or less, of trying to see whether that is a question that we want to answer, and can we convince scientists in other fields that it's worth doing and worth the investment.
Bjørn?
Yeah, maybe it's a question of
both.
Yeah, I mean, maybe it's a question of where the biggest problem is that scientists will try to solve. Right? This is called the How the Light Gets In Festival, and it's based on the lyric from Leonard Cohen that there's a crack in everything, that's how the light gets in. And when you look at the standard model of physics, it looks like there are very few cracks left in it. That's the impression that you're left with, because we run so many repeated controlled experiments that seem to say the same things. But when you look up in the sky, when you look at cosmology today, you see a lot of cracks in that field. So I'd be asking either of these physicists on my left and my right, what kind of experiments could be done, or what kind of observations could be done that could potentially reveal more interesting and more useful research, for example, in astrophysics rather than in theoretical physics or in particle physics.
Is there a limitation to doing both? Why does it feels very one or the other? Can these different schools of physics thought coexist?
Well, yeah, I mean, so in the end, I think it's a matter of money, but also of people. So you see, part of the problem is if we build this bigger collider, this will be a huge project, and it'll attract a lot of people that'll go into particle physics. And all those people which go into particle physics won't be available to work on other things. And if that's the right thing to do, then that'll be great, because it'll be a breakthrough and it'll be glorious. If it's the wrong thing to do, it'll just stall progress for another 50 years or something. So this is why I'm saying we need to think about it. Now, when it comes to astrophysics cosmology, we already talked about this in the earlier discussion. The issue is that it's often not that clear if what you're looking at is actually a fundamental question, or it's something about the modeling that we don't understand. For example, it's like galaxies are one of a kind. They're all different. They're not like particles. You know, one electron is like the other electron. So it's much easier to figure out if there's something new going on. Whereas if you're trying to understand galaxies, there's so many effects you need to take into account, you know, about what's with all those stars, what kind of stars, how old is the thing, did it collide with something? And it becomes really, really difficult to untangle the fundamental effects from observational effects, from modeling effects. There could also be modifications to gravity that, again, don't really have anything to do with the fundamental questions. So don't get me wrong, I'm super excited about what's going on in astrophysics, especially now with the Webb telescope that's telling us so many new things about the early universe and so on. But I don't really see it having a big impact when it comes to those fundamental questions.
Okay. Gavin, would you like to add?
Yeah, so one of the problems is you've got big questions and you really don't have a very good idea of how to get the answer to them. Dark matter is one of them. And you do want to look in as many places as possible. And you want to encourage people to try out new original ideas. And I don't think that's necessarily in contradiction with building big colliders. Colliders attract people. The fact that you're doing something big attracts people to the field, gets them interested. And then when they come along, they might discover other bits that they get interested in. So one of the things that actually happens is that some people get attracted by the ideas of particle physics and the ambitions of what particle physics is trying to do. And then they see how particle physics is done. Some of it is done in big experiments. You've got an experiment with 3,000 people. Some people love that. It's sort of a big team working all together. That's really the right environment for some people. And some people say, no, I can't work in a team of 3,000 people. I want to do something smaller. And there's a variety of people are different. So as long as if you're attracting people, then they will go off. Some will do the big experiments, and some will do the small experiments. You need to make sure there are resources in the system that both kinds of experiments can be done. But I don't think there's a contradiction.
But this idea of, for example, building a new collider, attracting particle physicists, and continuing that school of thought, do you think there's a chance in the future then that our current account of elementary particles could be radically overturned?
I think what's clear is that whatever we find, our current account will still be a good description for a lot of things. We found that over and over again. Atoms are still a good description of chemistry. Electrons, protons, and neutrons are still a good description of atoms. Each layer that you go onto, you haven't upended your original description. You've added a new dimension to it, a new perspective on it, and you've seen that maybe it comes from something else. So rather than revolutionizing or upending what we've got, it might help us understand why we've got what we've got. There's all sorts of mysteries. Why do the particles, we've got 17 particles, 12 of them, we really don't understand why their masses have the values they have. It just seems like a bunch of random numbers. Maybe we find something that actually gives us an explanation for that. Or maybe it actually is random.
Yeah. Sabine, do you agree with that?
Yeah, I agree with that. Though one should keep in mind that there might just be no explanation. Maybe they just have some random values, and that's the end of the story. I know that would be kind of disappointing. You know, you would certainly like to have an explanation. Why is the mass of the Higgs boson what it is? But the universe is under no obligation to provide that kind of explanation.
No. And here I would say I also agree with Gavin's assessment that I think the current description and the account that we have through the standard model, it's not likely to be radically overturned. It would only be if it happens in the context of a larger shift uniting both cosmology and particle physics into a wider frame of understanding. But that kind of revolutionary overturning is very different from searching for an even more ultimate particle or an even smaller constituent necessarily. Right? That is about how these things are connected.
I mean, we've talked a lot about shifts in thinking, whether we have the intention to encourage those shifts, whether we continue the way we've always been approaching physics or not. Do we have shifts ahead of us? Or are we quite happy with the way we are describing particles at this point in time? I don't know. Who shall I go to? I think Gavin.
We know there's problems. We know that we don't understand how to unify quantum mechanics and gravity. We know there are shifts out there to be had. The problem is, how do we get to the understanding? And we need either a brilliant idea, but people have been thinking about this for quite a long time, for 50, 60 more years, and not getting a good answer. We need guidance from experiment, and the question is, how do you probe this experimentally when the energy scales are so far beyond the point where we are probing directly experimentally today? Maybe something in cosmology might give us a clue. We're desperate for a clue. I think we need experimental evidence, and the question is how we get there.
I'm going to ask the question slightly differently. Sabine, do you think shifts are in our future in the way we define particles right now?
In the way we define particles, no, I don't think so. But I think there are other things that are going to shift. For example, how we think about those problems in cosmology. I don't think that a particle is the right answer to that. I think we need something else. And I also think, Gavin just said that we understand, the standard model just fine and so on. I'm somewhat surprised, actually, since you're working on quantum field theory. There are actually quite a few problems in quantum field theory that we don't understand, where I think there's theoretical work to be done, and those are actually very interesting questions. And I think that we have a lot of those niggly bits, in astrophysics and quantum field theory and quantum gravity and so on, that seems to me to hint towards a lack of understanding of what quantum physics is in the first place. And so this is where I think the next big breakthrough is going to be, that I hope we'll finally understand what all this quantum business is really about.
So Bjørn, we have less than 30 seconds, I reckon.
Oh, wow.
The niggly bits, can we address them the way we have always been addressing physics, or does something need to radically change, in your opinion?
In 20 seconds.
In 20 seconds. I mean, physicists are great at answering the niggly bits, right? Within its puzzle solving within the existing paradigm. The question about radical overturning that you started originally, I think, and I agree with Sabine, I think we're going to see shifts in cosmology, but it's hard to, at this point, to see that happening with the standard model of physics at the particle level.
Well, that brings us to the end of the time we have together. Thank you to an incredible panel for this really deeply fascinating debate. Thank you.